Welcome to the Mechanics of Solids lecture series. In this series of videos, we're solving examples for beam deflections by integration. The next example is a simply supported beam with a distributed load. We're asked to evaluate an equation for the deflection by integrating the second order beam differential equation, evaluate the peak deflection, and indicate where it occurs. I always like to start this problem by sketching the deflected shape. Here I'll do it right on the beam. Since the loading is symmetric, we have pin supports on the end. We know the ends are going to rotate. A peak deflection will occur in the middle, and the deflected shape will look something like that. Our procedure, we start by step 1, evaluate the moment function. First thing we need to do is solve for the beam reactions. Because we have simple supports, each support carries a vertical reaction. Because of the symmetry, they'll both carry half of the load, which is WL, so each reaction is WL over 2. To find the moment function, we make a cut somewhere in the middle of the beam. We draw a free body diagram of the left side of the cut. We replace the load, distributed load W, the reaction WL over 2. The distance is x because we're solving for the moment as a function of x, and we'll draw the unknown moment m of x in the positive direction. By summing the moments at point x, I can easily find that m of x equals negative wx squared over 2 plus WL over 2 times x, which is the contribution from the reaction. Step 2, we need to find our boundary conditions. Boundary conditions can be determined from the pin supports. They have to be conditions on deflection or rotation. Each of the pins, we know the deflection is equal to 0, so we can write that boundary condition as V of 0 equals 0. That stands for V at x equals 0, and V at x equals L, or V of L equals 0. Those are the boundary conditions we can use. Step 3, we will integrate the beam equation. So let's summarize the beam equation for this case. EI d squared V by dx squared equals m of x, which in this case is negative wx squared over 2 plus WL over 2 times x. Let's go to a clean screen. We have the beam equation and the boundary conditions. Let's integrate once. EI dV by dx equals negative wx cubed over 2 times 3 is 6 plus WL over 2 times x squared, so I'm going to 2 times 2 is a 4, plus a constant of integration, which I'll call C1. Let me integrate a second time. EI V of x equals negative wx to the 4th over 6 times 4 is 24 plus WL x cubed over 4 times 3 is 12 plus C1 x plus a second constant of integration, C2. Let's start with the easier boundary condition, which is V of 0 equals 0 is going to be equal to C2, so that tells us that C2 is equal to 0. Second boundary condition, V of L equals 0. We'll set that equal to negative W L to the 4th over 24 plus WL times L cubed. It's also WL to the 4th. Sorry, this should be L to the 4th over 12 plus C1 L equals 0. Okay, let's combine these two terms. A negative 1/24 plus 1/12 gives us 1/24 WL to the 4th plus C1 L equals 0. Therefore, C1 equals a negative WL cubed over 24. Okay, so here's our beam equation. V of x, or our deflection equation, V of x, I'm going to divide every term by EI, equals negative wx to the 4th over 24 EI plus WL x cubed over 12EI plus a negative WL cubed times x over 24EI. And I'm perfectly content to leave it in this form. No need to factor out common terms or reduce further. The last step in the problem is to find the peak deflection. Peak deflection is going to occur at the midpoint, or at x equals L over 2, so we'll evaluate the beam equation, the deflection, at x equals L over 2. V of L over 2 equals negative W over 24 EI times L over 2 to the fourth plus WL over 12 EI times L over 2 cubed minus WL cubed over 24 EI times L over 2. Okay, notice that every term has a WL to the fourth in it divided by EI. So I'm going to factor that out, WL to the fourth over EI, and I'm left with all the numbers. I have negative 1 over 24 times 1/2 to the power of 4, which is 1/16. Then I have plus 1/12 times 1/2 to the power of 3, which is 1/8. Then I have a minus 1/24 times 1/2. The most elegant way to handle this is to keep it in fractional form, and to do this I need to find the least common multiple. It turns out both of these second terms go into the first one, so this is the least common multiple, and it's 384. We multiply the second term times a 4 over 4, and we need to multiply the third term times an 8 over 8. So putting everything together, we have WL to the fourth over EI times negative 1 plus 4 minus 8 over 384. And this reduces to negative 1 plus 4 is 3 minus 8 is negative 5, reduces to negative 5 over 384 WL to the fourth over EI. If you use beam deflection tables and you look up this solution, you'll see that they provide it in this form. Another acceptable way to handle this is to take the numbers when they're in this form and punch them into your calculator. I don't prefer this, but it is acceptable if you have trouble reducing the fractions. If you plug it into the calculator, you'll get something like Vmax equals negative 0.013. I'm sorry, I think I have an extra 0 there. Negative 0.013 WL to the fourth over EI, and that's also acceptable. Okay, and that concludes this example.